The central limit theorem is a theorem that is going to be used throughout the rest of the semester. Let's consider our school campus and determine the average age. I want to know what is the average age of all COS students. Now here is the situation. Let's suppose we only had one day to do this. It is not possible to ask every single COS student. So we have a different plan. Let's suppose I take 5 individuals and calculate the sample mean. If I only done this once, the average might be close to the true average of all COS students, or it might be a little bit off. So we'll do this process again. You'll take another group of 5 individuals and calculate that sample mean again. We'll do it for another 5 individuals, and then we'll keep doing this process until we have a data set. Now the question is, are all of these sample means going to be exactly the same? Or all of the averages going to be the same? The answer to that is absolutely not. These are not going to be the same averages. Random sampling yields different results, and therefore each of these sample means is going to be different because they're different individuals. The central limit theorem is the most important theorem in statistics. That's right, it's the most important theorem in statistics. It has to do with the distribution of the sample mean and sampling error. Suppose I want to estimate the average age of students on campus. If I go out and take a random sample of 50 individuals, and you go out and take a random sample of 50 individuals, would our sample means be the same? Of course not, since each of us is sampling randomly, and therefore we would most likely get different people in our samples, and thus get individuals with different ages. This difference due to random sampling is called sampling error. Now let's suppose that we go out and take 100 different random samples, and for each one we calculate the average age. This would produce a new data set of 100 values. This new data set consisting of 100 sample means is called a distribution of the sample mean. Of course, we could take more than 100 samples if we desired. The question is, what does this new data set look like? What is the shape? And what properties does it have? To learn more, let's watch a YouTube video on the central limit theorem.
Somewhere in the fields, a brave ecologist is studying wild rabbits. He plans to record the weights of every single rabbit. If he follows this plan, he will notice that most of the rabbits are close to the average, and that there are some rabbits, but not many, that are much larger or much smaller than the average. The further from the average you get, the fewer animals there are. This particular bell-shaped curve is called a normal distribution. Sadly, he has to give up his experiment, for it will cost him a fortune in carrots to complete it. So, he changes the plan. Instead of measuring every rabbit in the whole group, he decides to measure rabbits in small groups, chosen at random from the whole group. He knows that each small group won't necessarily be perfectly representative of the whole group, so he measures many small groups and then compares the averages of each. He starts by weighing 5 rabbits at a time, and he finds that the distribution of the average is somewhat bell-shaped. Then he increases the sample size by weighing 20 rabbits at a time, and then 100 rabbits at a time. Surprisingly, as the sample size increases, the spread decreases. The distributions of average weights becomes more and more normal. What our brave ecologist has just demonstrated is the central limit theorem. The averages of samples have approximately normal distributions. If the sample size increases, this distribution of averages becomes more normal and narrower. What if the population distribution is not normal to begin with? For example, the distribution of dragon wingspan is known to be bimodal. If an even braver ecologist were to study wild dragons and measure dragon wingspans, the distribution of the average wingspan would still be approximately normal. And again, the more dragons our brave ecologist could measure at a time, the closer the distribution of their average wingspans will be to a truly normal distribution. The distribution will also be narrower. So now we know that regardless of a true distribution, the central limit theorem shows that the average of values drawn from the distribution will always be approximately normal. Furthermore, the bigger the sample size, the narrower the distribution of average becomes, and the closer the mean of the sample gets to the true mean of the population. This is why sample size matters so much in any statistical analysis, whether it is a political poll or evaluation of a medical procedure.
In summary, regardless of the distribution or shape of the population, the distribution of the sample means is approximately normal if the sample size is sufficiently large. This approximation improves as the sample size increases. Note, the sample size required will depend on the underlying population. The more normal the population looks like to begin with, the smaller the sample size we'll need before we start to see results. In fact, the sample mean has a normal distribution for all sample sizes if the population is itself normal. Thus, under certain conditions, the distribution of the sample mean will be approximately normal, perfectly bell-shaped and symmetrical, and it has these two properties. The first one, the mean of the sample means is equal to the mean of the population. The second property is the standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of the sample size. We also call the standard deviation of the sample means as the standard error. Note, the central limit theorem does not say that if n is large, then the sample is normally distributed. It is the sample mean that is normal, not the sample itself. It doesn't matter if the population is not normal, we're saying the sample means will be normal.